everyone! In this video we are going to learn about the dot product. So this has to do with vectors. Now we're going to consider the angle between two vectors, and these two vectors have the same initial point. Okay, so they start in the same place. So if we just draw that real quick, let's say we have this vector u, and at the same starting point we have another vector v, and so the angle between them, let's draw that. We're going to use theta to represent that angle, and I'm just going to say that theta is between 0 and pi. Okay? If we were to go beyond pi, or 180 degrees, it would basically be the same angle, just kind of starting over if you were to go like down there. Anyways, theta is between 0 and pi. Okay, so dot product, it's going to come up after this theorem. So there's a theorem that says the following. If I have two vectors, u and v, but let me give you the components. So I'll say if u is the vector with components u1, u2, u3, and v is equal to the vector with components v1, v2, v3, then the following is true. So then the angle between them, so I'm just going to say theta since I already drew it here, the angle between them equals this: cosine inverse of this pretty big fraction here, where the numerator is u1 times v1 plus u2 times v2 plus u3 times v3. Okay, and then the denominator is the magnitude of u times the magnitude of v. It looks like a lot, and so the dot product is going to be a nicer way for us to write this numerator. So the angle between two vectors, that's what this is saying. Between these two vectors, the angle formed between them equals this quantity here, cosine inverse of this expression. Okay, so then the dot product is the following. It's just this numerator. So here's how we denote it, and it's going to look similar to multiplication, but just be aware if I draw a dot this large, I mean dot product. Okay, so u dot v is how you would read this. U dot v. And it equals the first component of u times the first component of v plus the second component of u times the second component of v plus the third component of u times the third component of v. Now what I want you to recognize here is that when you take the dot product of two vectors, because you're multiplying and adding the components, this is a number. So this is a number. The dot product is a number. In the very next section we'll learn about cross product, which is a vector. Dot product, every time you do it, you're going to get a number. Okay. Alright, so then we can rewrite our formula here. Let me go ahead and move it up here. Our formula for the angle between two vectors can be rewritten a little bit nicer. So then theta is cosine inverse of this whole numerator is just u dot v over then the denominator, magnitude of u times the magnitude of v. Okay, so another way to write your angle between the two vectors, now using this nice idea that you just learned, dot product. There is another form that you can use. So the other form, so I'll say or, another form for this, let's go ahead and get rid of that drawing. We have that u dot v can be written as the magnitude of u times the magnitude of v times cosine of theta. Alright, so you have two things here, two versions. Here's one version of the dot product. This one you'll use pretty often. Right there. This one is useful if you know u and v in terms of their components. So you would use this version. But notice I'm telling you also that the dot product is this. This would be more useful if, let's say, you didn't quite know the components of the vectors. You didn't know the terminal point of the vectors, which would be these components here. But you did know how long the vectors were, their magnitude, and you already knew cosine of the angle between them. This would be more meaningful for you. Okay, so two different tools or two different ways to find the dot product. You pretty much just pick one or the other based on what you know. Now let me just kind of give you some facts about it, more so visually more than anything, about the angle and then the resulting dot product. So let's say we had an acute angle between our vectors. So we'll say if, and we'll draw this as u and v like this. Okay, we'll say that this is our theta, and so theta is acute, meaning it's between 0 and 90. So 0 and 90, or you could say pi over 2. Okay, if this is true, your dot product then, that means that u dot v is going to be positive. Okay, and you can compute this. See, the things I'm about to tell you, you don't have to memorize. It's just to kind of give you a summarization of it. But you can compute the dot product and you'll see that you'll get a positive answer when your angle's between 0 and 90. Well, what if your angle is bigger than 90? So this is obtuse. So this is u, this is v, theta's over there. And so theta is greater than 90, or greater than pi over 2, but less than pi, or 180. Well, in that case, the dot product is negative. So u dot v is less than 0. Okay, so now you might already figure this out. What if theta is 90? So what if your angle between your two vectors is exactly 90 degrees? Well, you probably guessed it. 0, your dot product. So theta equals 90. So u dot v equals 0. And so this one, you can kind of work both ways. Let's say you knew that the angle between your vectors was 90. You could say the dot product's 0. Or if you knew that you had two vectors and somehow you were told, or you knew the dot product was 0, you can then say, well, they must be perpendicular to one another, 90 degrees between them. So you can, let's put this as a fact over here. Orthogonal, which is another word for perpendicular. Orthogonal, if you want to put perpendicular next to this, so you know, orthogonal vectors, we'll say implies that their dot product is 0. We'll put it in words. Dot product equals 0. Alright, this is our fact. So again, you can go back and forth. I'll put it like this. Double-sided arrow. Dot product 0, vectors are orthogonal. Orthogonal vectors, dot product is 0. And remember, one more time, perpendicular, 90 degrees between them. That's orthogonal. Okay, let's see. Two more for you, two more facts right there. We have that the vectors actually point in the same direction. So let's say that I have vector u, it looks something like this, and then vector v, let's just pick a new color, is pointing the same way. It's parallel. So v is parallel to u. Let's go and put that vector notation on. Then, in this case, the dot product is actually the product of the magnitudes. Okay. And you can work it out component-wise if you knew the components, and you'll get this answer anyway, but this is just a nice fact. So if you know that the vectors are parallel, they're pointing the same way, then this is their dot product. And then our last fact of this kind, if our vectors are actually parallel but pointing in opposite directions, so let's say u points this way, and then we'll say v points this way, then the dot product is very similar to the last one, but the negative of it. So negative of the magnitudes being multiplied. And that's if they point in different directions but are still parallel. All right, now let's give an example so you can see this idea in use. Okay, so I'm going to let the vector u be the vector with components square root 3, comma 1, comma 0, and then the vector v is going to be the vector with components 1, comma square root 3, comma 2 square root 3. Now we're going to find a few things. First, we'll call it part A. Let's go ahead and find the dot product of u and v. Okay, well, you had two formulas for dot product we just went over. One required that we knew the angle and the magnitudes. We don't know anything about the angle between these vectors, but we do know the components, so we're going to use that version of the formula. So this dot product, u dot v, is just going to be the components multiplied and added. That was our formula. So components multiplied, respectively, x times x, y times y, z times z, and then added. So square root 3 times 1, and then plus 1 times this square root 3, and then plus 0 times 2 square root 3. And just like I told you, you're going to get a number answer. So notice this is the number. And so if we simplify this, this is square root 3 plus square root 3 plus 0, which is 2 square root 3. Final answer. So the dot product between these two vectors is 2 square root 3. Let's go ahead and do a part B to this. We are going to find the angle. Let's move up here. The angle between these vectors. Okay, so part B. Find the angle, and you could just call it theta if you want, between u and v. Alright. So, we have a formula for that. Let's see what we have. We just have the components here. We have the dot product. We've actually done like almost half the work for the angle formula. If we go back, we know that theta, the angle between the vectors, is equal to cosine inverse of the dot product over the magnitudes being multiplied. So we've done the numerator. So this is cosine inverse of 2 square root 3 on top. And then on bottom we do have to find these magnitudes. So let's go ahead and do that off just right underneath, and then we'll plug it into the formula. So this is like my side work. So the magnitude of u, remember your magnitude formula, you just take the components, square them, add them, and then take the square root. So this is square root of 3 squared plus 1 squared plus 0 squared, which is going to be 3 plus 1, so square root of 4, which is 2. Okay, so this right here is 2. And then times, let's change colors here. We'll go right over here. Magnitude of v, square root of 1 squared plus square root 3 squared plus 2 square root 3 squared. Okay, and so that's going to be 1 plus 3. Let's actually write this out. 1 plus 3. This is going to be 4 times 3, so 12. So 12 plus 3 plus 1. This is square root of 16, which is 4. So this is 2 times 4. And then put that together. We can actually divide out the 2's there. So this is cosine inverse of square root 3 over 4. And that's theta. So that's the exact answer. Let me go ahead and put it down here. This is our original. Let's see. Leave that there. So theta is exactly cosine inverse of square root 3 over 4. Theta is about 1.12 if you're in radians and about 64.3 degrees in degree mode. Alright, so that is and you finding the dot product and then also finding the angle between two vectors. Alright, so now I'm going to tell you about some properties of dot product. Now my fine print here is just that U, V, and W are going to be my letters for vectors, and then the letter C will be reserved for a scalar or constant. So these properties you're going to find are pretty intuitive for the most part. At least some of them will be pretty straightforward. U dot V is equal to V dot U. Alright, so when you multiply two vectors, or with the dot product, excuse me, when you dot two vectors, is how I should say it, it's commutative, meaning you can change the order and get the same answer. Number two, let's say I have a scalar times my vector, U, and then I dot that with V. Well, that's the same as if I said U dot C times V, which is the same as C times U dot V. You can basically associate any two parts of this together and get the same answer. Times U by C first, times V by C, or times both by C after the dot product is done. Same answer all the way across. Number three, U dot the quantity V plus W is the same as, and this one looks like distribution, U dot V plus U dot W. Okay, so you're dotting these, but it's like what you know about distribution with multiplication. Number four, U dotted with itself. So if you take a vector and you dot it with its same vector by itself, what you end up with is just the magnitude squared of that vector. And so a nice consequence of this is if you want just the magnitude of the vector, well, it's the square root of this. So it would be the square root of U dot U. So you can use two versions of this one. And then number five here, the zero vector dotted with U equals the number 0. So remember, dot product equals a number. So when you dot zero vector with the vector U, zero vector dotted with U, you get the number 0, the scalar 0. Alright, so that's it for this one. In the very next video, we're going to talk about vector projections.